tonight, we will drift for a little while outward, beyond the familiar quiet of a darkened room, and into a different kind of quiet, a silence that is ancient and deep and filled with a soft and distant light. We will explore the cosmos, not as a complex problem to be solved, but as a vast and peaceful landscape. Let us begin our journey. There is a thought, a simple comparison, that helps to frame the sheer scale of our universe. It begins on Earth, on a familiar shore. Imagine standing on a beach, at the edge of a calm ocean. The air is still, the moon is full, and the only sound is the gentle, rhythmic whisper of waves sighing against the sand. If you were to reach down and scoop a handful of that sand, you would hold thousands, perhaps tens of thousands of tiny, individual grains. Each one a miniature stone, worn smooth by the endless patience of the water. Now, imagine trying to count them all, every grain in your hand. Then every grain on that single beach, a task that already feels impossible, a number that slips into the abstract. Expand that thought further. Imagine every beach on Earth, from the volcanic black sands of Iceland to the sun-bleached white shores of the tropics. Every coastline on every continent. Then, add to that, all the sand in all the deserts. The vast, rolling ergs of the Sahara, the silent, ochre dunes of the Namib, the great, sandy seas of the Arabian Peninsula. An ocean of sand, stretching for millions of square miles. And finally, consider the sand on the floor of the ocean itself. The immense, unseen plains of the abyssal deep. The silt and sediment, carried by rivers for eons, settling in the silent, crushing dark. If you could somehow gather all of it, every single grain of sand from our entire planet, and hold that impossible number in your mind, it would still be less than the number of stars in our observable universe. The mind struggles to hold an image of such magnitude. For every tiny, tangible piece of our world's geology, there is a distant, fiery sun, a blazing sphere of incandescent plasma burning across the void. Each of those stars, each point of light, is a furnace of immense power. In its core, the pressure is so great, the temperatures so high, that the very atoms of the universe are fused together. Hydrogen, the simplest and most abundant element, is crushed by gravity with such violence that it transforms. It becomes helium. And in that transformation, that alchemical fire, a tiny fraction of matter is converted into pure energy. A flash of light, a photon. This is the engine of a star, a process of continuous, controlled, thermonuclear explosion lasting for millions, or billions, or even trillions of years. The light born from that stellar heart begins a long journey. It fights its way out from the star's dense core, a process that can take 100,000 years, bouncing from atom to atom, absorbed and re-emitted, until it finally breaks free from the surface. And then it leaps into the vacuum of space. It travels outward, a silent, weightless messenger, carrying the story of its birth. This is the light we see when we look up at the night sky. Not just light, but ancient light. The star you see twinkling may be 1,000 light years away, which means the light reaching your eye tonight began its journey 1,000 years ago. When it left its star, cathedrals were being built on Earth, and empires were rising and falling. All the while, that tiny photon was silently crossing the immense, empty darkness. And the stars themselves are not all the same. They are a celestial menagerie of breathtaking variety. There are the colossal blue supergiants, monsters of the cosmos, hundreds of times larger than our own sun. They burn with a fierce, unimaginable intensity, their surfaces raging at temperatures of tens of thousands of degrees. They live fast, and they die young, burning through their vast reserves of fuel in just a few million years, before collapsing and exploding in the glorious and violent detonations we call supernova. Then there are the stars like our sun, yellow dwarfs, stable and calm and incredibly long-lived. They are the gentle hearths of the galaxy, providing steady, reliable light for billions of years, making them ideal candidates for nurturing the slow, patient evolution of life on orbiting planets. And there are the red dwarfs, the most common type of star in the universe. They are small and dim and cool, scarcely larger than the planet Jupiter. They sip their hydrogen fuel with an almost impossible efficiency. They burn with a gentle, ruddy glow, and their lifespans are measured not in billions, but in trillions of years. Long after our sun has exhausted its fuel and faded away, long after the great blue giants have exploded and vanished, the little red dwarfs will still be shining like cosmic embers in the deep twilight of the universe. And this vast, uncountable number of suns, this ocean of stars that outnumbers the grains of sand, suggests another, even more profound idea: the idea of possibility. For most of the stars we see are not solitary. They are the center of their own systems. As these stars are born, they are surrounded by vast, spinning disks of leftover gas and dust. And within these protoplanetary disks, gravity begins its slow and patient work. Dust grains stick together, becoming pebbles. Pebbles collide, becoming boulders. Boulders accumulate, becoming planetesimals, and then, over millions of years, these grow into planets. Rocky worlds close to their stars' warmth. Giant balls of gas and ice in the cold outer regions. So when we consider that cosmic census, the stars outnumbering the sand, we are also considering the potential for worlds without number. Planetary systems, each one unique. Each star a potential anchor for its own family of planets. It's a thought that dissolves our sense of centrality and replaces it with a feeling of profound connection, a humbling and quiet awareness of just how vast and rich and full of possibility the universe truly is. An endless ocean of light, of energy, and of potential worlds, stretching far beyond the limits of our imagination. The light from these countless stars travels, and eventually it reaches us. But there is a boundary to what we can see. A horizon, not of space, but of time. Our observable universe, the sphere of everything we can possibly detect, stretches about 93 billion light years from end to end. To understand that number, we must first understand its unit of measurement. A light year. It sounds like a measure of time, but it is a measure of distance. The greatest distance imaginable. It is the distance that a particle of light, a photon, travels in a single Earth year. Light moves at the ultimate speed limit of the cosmos, roughly 186,000 miles or 300,000 kilometers every single second. In 1 second, a beam of light can circle the Earth more than 7 times. In the space of a lazy heartbeat, it can travel from the Earth to the Moon. In about 8 minutes, it can make the journey from the surface of our Sun to us. Now, imagine that photon continuing its journey for an entire year. Never stopping, never slowing. Crossing mile after silent mile of empty space. The distance it covers in that year is nearly 6 trillion miles or 10 trillion kilometers. That is 1 light year. And our observable universe, the bubble of reality accessible to our telescopes, is 93 billion of those units across. It is a scale so far beyond human experience that analogies begin to fail. But we can try. If our entire solar system, out to the orbit of Neptune, were the size of a single coin, the observable universe would be larger than the entire planet Earth. It is an immensity that is layered and deep, filled with structures of unimaginable size. But why is there a limit? Why 93 billion light years? It's not because space ends there. There is no wall, no physical edge. The boundary exists because the universe itself has a finite age. We know from a wealth of evidence that our cosmos began about 13.8 billion years ago in a hot, dense state we call the Big Bang. Since that moment, it has been expanding. So, light from the most distant objects has only had 13.8 billion years to travel towards us. Anything further away than that, the light simply hasn't had enough time to complete its epic journey and reach our telescopes. So our cosmic horizon is a horizon in time. Looking out into the distance is the same as looking back into the past. When we look at the Andromeda Galaxy, our nearest major galactic neighbor, we see it as it was 2.5 million years ago. When we look at the most distant galaxies our best telescopes can detect, we are seeing them as they were over 13 billion years ago. We are seeing the universe in its infancy. Faint, reddened smudges of light that were among the very first structures to form. You might wonder, if the universe is 13.8 billion years old, why isn't the observable universe just 27.6 billion light years across? That is 13.8 billion in one direction and 13.8 billion in the other. The reason it's so much larger, 93 billion light years, is because of one of the most fundamental truths about our cosmos: space itself is expanding. While that photon from a distant galaxy was traveling towards us, the space it was traveling through was stretching. So the journey was much longer than it would have been in a static universe. The galaxy that emitted the light 13 billion years ago was much closer to us when the light began its journey. But during those 13 billion years, the expansion of space has carried that galaxy much farther away from us. It is now, today, an estimated 46.5 billion light years away from us. This leads to a profound and slightly melancholy thought. Beyond this visible boundary, this horizon of light, space almost certainly continues. It may even continue infinitely, filled with countless more galaxies, more stars, more mysteries. But we will never see them. The light from those impossibly distant realms is traveling towards us, but the space between us and them is expanding so fast that the light can never overcome the gap. It is like a runner on a treadmill that is speeding up. No matter how fast they run, the finish line moves away even faster. These galaxies beyond our horizon are forever out of reach, hidden from us, not by some cosmic veil, but by the very nature of space-time itself. It is a humbling reminder of our limits. The universe is not just what we see. What we see is just our local pond in an ocean that may be truly endless. Every observer, on every planet, in every galaxy, has their own observable universe, their own unique bubble of vision, with themselves at the center. And all of them are likely seeing just a tiny fraction of the whole, magnificent, and silent reality. This stretching of the cosmos is one of its most defining characteristics. Space itself is expanding, and it carries the galaxies along with it, moving them farther and farther apart with every passing moment. It's a common misconception to imagine galaxies as if they are ships flying through a pre-existing sea of space. That is not quite right. The reality is more subtle and more profound. The sea itself, the very fabric of space-time, is expanding. The classic analogy is to imagine dots drawn on the surface of a balloon. The dots represent galaxies. As you inflate the balloon, the rubber surface stretches. And as it stretches, the distance between every dot increases. It's not that the dots are moving across the surface of the balloon. It's that the surface itself is expanding and carrying the dots with it. From the perspective of any one dot, all the other dots appear to be moving away from it. And the farther away a dot is, the faster it appears to recede, because there is more stretching balloon surface between them. This is precisely what we observe in our universe. When we look at distant galaxies, we see that they are all moving away from us. And the farther away a galaxy is, the faster it is moving away. This isn't because we are at some special, central point. An observer in any of those distant galaxies would see the exact same thing. They would see our Milky Way and all other galaxies moving away from them. In an expanding universe, everyone gets to feel like they are at the center. This cosmic expansion is a slow but relentless process. It happens everywhere, at every moment. It is woven into the very mathematics that describe our universe. On smaller scales, like within our solar system, or even within our own galaxy, the force of gravity is strong enough to overcome this expansion. The stars in the Milky Way are gravitationally bound together, so our galaxy is not expanding. The Earth is not getting farther from the Sun. But on the vast, intergalactic scales, the scales between clusters of galaxies, this gentle, persistent stretching of space-time is the dominant force. It is the grand, overarching dynamic of the cosmos. It affects how light travels, stretching its wavelength and making distant objects appear redder. It dictates the large, scale architecture of the universe, shaping the great voids and filaments of the cosmic web. And ultimately, it will determine the final fate of the cosmos. This slow, silent, and inexorable growth of everything is the quiet rhythm to which the entire universe dances. This constant, gentle expansion of the universe naturally leads our thoughts backward in time. If everything is moving apart now, it must mean that in the distant past, everything was closer together. Much, much closer. If we rewind this cosmic film, we see the galaxies rushing back towards each other. The vast voids between them shrink. The universe grows smaller, and denser, and hotter. We rewind past the formation of the first stars, past the era when the cosmos was a glowing fog of plasma, past the first few minutes when the simplest atomic nuclei were forged. We keep rewinding all the way back to the very first moment. A point in time, 13.8 billion years ago. This moment is what we call the Big Bang. And here our language and our imagination begin to falter. The term itself, Big Bang, is a wonderful piece of cosmic poetry, but it is also profoundly misleading. It conjures an image of a colossal explosion, like a bomb detonating at a single point in a pre-existing empty space. A fireball expanding outward into a dark, silent void. But that is not what happened. The truth is far stranger and more magnificent. The Big Bang was not an explosion in space. It was the beginning of space. It was not an event that happened in time. It was the beginning of time. Before this moment, the concepts of before and space and outside simply had no meaning. There was no void for the universe to expand into. There was no clock ticking to measure the moments leading up to it. All of the space, all of the matter and energy, and even time itself, was contained within a state of almost unimaginable nature, a singularity, a point of infinite density and infinite heat. It's a concept that pushes the boundaries of our physics, a place where our known laws of nature break down. But we can try to picture it in abstract terms. Imagine all the vastness we've just considered. The 93 billion light-year-wide observable universe. Every one of the uncountable stars. Every galaxy, every nebula, every planet. All of the matter and all of the energy. Now, imagine all of that substance compressed. Not just into a small room or the head of a pin, but compressed into a region smaller than a single atom. Infinitely smaller. And it wasn't just the matter that was compressed. It was space itself. The very idea of location. Every point in our vast universe today was once the same point. The place where you are now, and the location of the most distant galaxy we can see, were, for that briefest of instants, occupying the same infinitesimal position. Then, for reasons we do not yet fully understand, it began to expand. From this state of pure, undifferentiated potential, space-time unfurled. It was not a violent outward blast, but a smooth and rapid, and utterly comprehensive unfolding of reality itself. Space did not expand into anything. Space was the thing that was expanding. In the very first fractions of a second, the universe was a seething, incandescent soup of fundamental particles and energy. The temperature was trillions upon trillions of degrees. The four fundamental forces of nature that we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were all thought to be merged into a single, unified super force. As space expanded, it cooled. And as it cooled, this unified force began to fracture or freeze out, one by one. Gravity separated first, then the strong nuclear force, then the weak and electromagnetic forces. Each of these moments, these phase transitions in the early universe, unleashed enormous amounts of energy and fundamentally changed the rules by which matter and energy could interact. It was during this primordial era that time itself began to have meaning. The cosmic clock started to tick. The relentless expansion, the stretching of the fabric of reality, was underway. This initial, rapid growth set in motion the entire chain of events that would eventually lead to the formation of atoms, of stars, of galaxies, and eventually to a small, quiet planet, orbiting a stable, yellow star. It is a concept that truly stretches our understanding. An origin story, not of a place, but of placement itself. The birth of the very stage upon which all of cosmic history would be performed. The echoes of this primordial beginning are not lost to time. They are still here, all around us. In every direction we look, filling every cubic centimeter of space, is a faint and ancient light, a whisper of radiation from the dawn of time. It is called the cosmic microwave background. To understand this light, we must journey back in our minds to the young universe. For the first few 100,000 years after the Big Bang, the cosmos was a very different place. It was still incredibly hot and incredibly dense, but it was also opaque. A glowing, cosmic fog. The universe was filled with a plasma of fundamental particles, protons and neutrons, and electrons swirled in a chaotic, energetic dance, and also photons, the particles of light. But these photons couldn't travel very far. Every time a photon tried to move, it would immediately slam into a free, floating electron and be scattered in a random direction. Like a pinball in an infinitely dense machine, light was trapped, tethered to matter. The universe was hot and bright, but you wouldn't have been able to see anything within it. It was a uniform, blinding haze. For about 380,000 years, this was the state of the cosmos, but all the while, space continued to expand. And as it expanded, it cooled. The universe was becoming more and more dilute. Eventually, it reached a critical temperature, about 3,000 degrees Celsius or 5,000 degrees Fahrenheit, roughly the temperature of the surface of our sun. At this temperature, the universe was finally cool enough for something remarkable to happen. The protons and electrons, which had been flying around freely, now had low enough energy to be captured by each other. Electrons settled into orbits around protons, forming the first stable, neutral atoms of hydrogen. This event is known as recombination. Suddenly, with the free electrons now bound up inside atoms, the photons had a clear path. The fog lifted. The universe, for the very first time, became transparent. The light that had been trapped within the plasma was now released, and it flooded the cosmos, traveling freely in all directions. That light, that very first light to travel unimpeded through the universe, is still traveling today. It has been traveling for nearly 13.8 billion years. And in that time, the relentless expansion of the universe has had a profound effect on it. As space itself has stretched, the wavelengths of this ancient light have been stretched along with it. What was once a bright, visible glow, like that of a hot star, has been stretched out, or red-shifted, all the way into the microwave portion of the electromagnetic spectrum. So now, it is a faint, cold glow, invisible to our eyes, but detectable by sensitive radio telescopes. It is the cosmic microwave background, or the CMB. It is the afterglow of creation, the oldest light in the universe. When we map this light across the sky, we are looking at a photograph of the universe as it was when it was just a baby, an infant snapshot from 380,000 years after its birth. It is astonishingly uniform. The temperature of this background radiation is almost the exact same temperature, just 2.7 degrees above absolute zero, no matter which direction we look. This incredible uniformity is powerful evidence that the universe did indeed begin in a hot, dense, and mixed state. But it is the imperfections, the tiny, almost imperceptible variations in this uniformity that hold the most profound story. When we look with incredibly sensitive instruments, we find that the CMB is not perfectly smooth. There are minuscule fluctuations in its temperature, tiny patches that are a few millionths of a degree warmer, or a few millionths of a degree cooler than the average. These tiny ripples are the seeds of everything that exists today. The slightly warmer, denser patches were regions in the early universe where there was just a tiny bit more matter. Over the next billion years, the relentless pull of gravity would work on these subtle imperfections. The denser regions would pull in more and more matter from their surroundings. They would grow and condense, and slowly, Over immense stretches of time, they would collapse to form the first stars, the first galaxies, and the great clusters of galaxies we see today. The slightly cooler, less dense regions would become the great cosmic voids, the vast, empty spaces between the galactic filaments. So, this faint, silent microwave glow that fills every corner of space is a treasure map. It is a blueprint of the modern cosmos, seen in its embryonic form. A silent messenger from the dawn of time that not only tells us about our origins, but also carries the subtle, prophetic whispers of the entire grand structure of the universe to come. It surrounds us, passes through us, and connects us directly to the first moment that the universe stepped out of the fog and into the light. This cosmic blueprint, the faint ripples in the ancient light, tells a story of how matter began to clump together. But when we look at the galaxies and clusters that form from these seeds, we encounter a profound mystery. The matter we can see, the stars, the gas, the dust, everything made of atoms, is not enough. When we observe a galaxy, like our own Milky Way, we can measure how fast its stars are orbiting the galactic center. Stars farther out should be moving more slowly than stars closer in, just as Neptune orbits the Sun much more slowly than Mercury. This is what Newton's law of gravity predicts. But when we actually measure the speeds of these stars, we find something astonishing. They are moving far too fast, especially the stars on the outer edges of the galaxy. They are whipping around the galactic center at such incredible velocities that the gravity from all the visible matter, all the stars and gas we can account for, should not be strong enough to hold onto them. The galaxy should fly apart. It should have disintegrated billions of years ago. The same is true for clusters of galaxies. When we observe these immense cosmic cities, we see individual galaxies moving within the cluster at speeds so high that the gravity from all the other visible galaxies in the cluster is not nearly sufficient to keep them bound together. The cluster should be a chaotic, dissolving cloud, and yet it is not. Galaxies are stable. Clusters are gravitationally bound. There must be something else there, something we cannot see. A vast amount of extra mass, providing the extra gravitational pull needed to hold these structures together. This mysterious, unseen substance is what we call dark matter. The name is elegantly descriptive. It is dark because it does not seem to interact with light in any way. It does not emit light like a star. It does not absorb light like a dark cloud of dust. It does not reflect light like a planet. It appears to be completely transparent. Light passes right through it, as if it isn't there at all. And it is matter. Because it has mass, it exerts a gravitational force. And that gravitational pull is its only signature, the only way we know it exists. We detect it, not by seeing it, but by observing its gravitational effects on the things we can see. The fast, spinning stars in a galaxy, the tightly bound galaxies in a cluster. Even the way light from distant objects is bent and distorted as it passes through a region of space. An effect called gravitational lensing reveals the presence of a huge, invisible scaffold of mass. And the amount of this dark matter is staggering. Calculations based on all these different lines of evidence all point to the same remarkable conclusion. Dark matter makes up about 85% of all the matter in the universe. The familiar, atomic matter that makes up you, and me, and the Earth, and the Sun, And all the stars you can see in the night sky, all of that is just the tip of the cosmic iceberg. About 15% of the total. We are the anomaly. The universe, it seems, is dominated by a form of matter whose nature remains one of the greatest unsolved mysteries in science. We don't know what it is. It is not just ordinary matter that is cold and dark. It has to be something fundamentally different. Some new, undiscovered type of particle. Something not described by our current standard model of particle physics. Physicists have proposed many candidates, from tiny, lightweight particles called axions, to more massive, slow-moving particles called BULIMPs, or weakly interacting massive particles. Around the world, in deep underground laboratories, shielded from cosmic radiation, incredibly sensitive experiments are underway, trying to catch the faintest whisper of a dark matter particle passing through their detectors. So far, they have found nothing, but the evidence of its existence is etched into the very structure of the cosmos. Dark matter forms a vast, invisible framework, a cosmic web of filaments and halos that stretches across the universe. The galaxies we see are like glowing jewels strung along this unseen scaffold. The visible universe is just the luminous foam on a deep and invisible ocean of dark matter. It is the hidden architecture, the silent gravitational skeleton, that holds our universe together. Just as we begin to acclimatize to the idea of this vast, invisible scaffolding of dark matter, the cosmos presents us with an even deeper and perhaps more consequential mystery. If dark matter is the silent, gravitational glue holding galaxies together, there is another, even more dominant force, doing the exact opposite. A mysterious energy, pushing the universe apart and causing its expansion to speed up. For most of the 20th century, cosmologists had a clear expectation for the future of the universe. After the initial impetus of the Big Bang, the expansion should be slowing down. It seemed like simple, cosmic logic. The universe is filled with matter, and matter has gravity. Gravity pulls things together. Therefore, the mutual gravitational attraction of all the galaxies and all the dark matter should be acting as a cosmic brake, gradually slowing the expansion over eons. The great question was whether there was enough matter, enough gravity, to eventually halt the expansion completely and cause the universe to collapse back in on itself, in a fiery, big crunch. Or if the expansion would slow, but never quite stop, leading to a future where the universe would expand forever, but at an ever-decreasing rate. Imagine throwing a ball into the air. Gravity immediately starts to slow it down. It might fall back to Earth, or if thrown with enough force, it might escape Earth's gravity, but it will always be slowing down. This was the model for the cosmos. To measure this expected slowdown, astronomers needed a way to look deep into the past and chart the expansion rate of the universe over billions of years. To do this, they needed standard candles. A standard candle is a celestial object whose true, intrinsic brightness is known. If you know how bright something truly is, you can determine how far away it is just by measuring how dim it appears. It's like seeing a 100-watt light bulb in the distance. The dimmer it appears, the farther away you know it must be. The perfect standard candles for this cosmic task were a specific type of exploding star known as a Type I supernova. These are not the typical explosions of massive, dying stars. A Type I supernova has a much more precise and reliable origin. It begins with a small, dense, dead star called a white dwarf. An ember left over from a sun-like star that has exhausted its fuel. If this white dwarf is in a binary system, orbiting with another star, its powerful gravity can begin to siphon off gas from its companion. For millions of years, it steadily pulls matter onto its surface, like a silent cosmic vampire. The white dwarf grows heavier and more compressed, until it reaches a critical mass, a precise, universal limit known as the Chandrasekhar limit, which is about 1.4 times the mass of our Sun. At this exact point, the pressure and temperature in the core of the white dwarf becomes so extreme that a runaway thermonuclear reaction ignites, all at once. The entire star detonates in a cataclysmic and breathtakingly brilliant explosion. Because they all explode at the exact same mass, these type Ia supernovae all reach almost the exact same peak brightness. They are astonishingly reliable standard candles. For a few weeks, a single one of these explosions can outshine an entire galaxy of billions of stars. They are so bright, they can be seen across billions of light years. In the late 1990s, two independent teams of astronomers set out to use these supernovae to measure the cosmic slowdown. They used powerful telescopes to find these distant explosions and carefully measured their faintness to calculate their distance and their redshift, to calculate how fast they were moving away. They were looking for proof that the universe's expansion was decelerating. They expected to find that the very distant supernovae, the ones whose light had traveled for billions of years, were slightly brighter than their redshift would suggest. This would mean they were closer than expected, which would prove that the expansion had been faster in the past and had slowed down since then. But they found the exact opposite. The results were shocking, stunning, and at first unbelievable. The distant supernovae were not brighter than expected. They were dimmer, significantly dimmer. There was only one way to interpret this. If they appeared dimmer, it must mean they were farther away than all the models predicted. And the only way they could be farther away is if the expansion of the universe, in the billions of years since those stars exploded, had not been slowing down. It had been speeding up. The cosmic ball was not falling back to Earth. It was accelerating away, as if propelled by some invisible rocket engine. This was a discovery that overturned decades of cosmological thinking. It was so profound, it earned its leaders the Nobel Prize in Physics. And the mysterious force, or energy, driving this cosmic acceleration was given a name as enigmatic as its nature: dark energy. Like dark matter, the name simply reflects our ignorance. We don't know what it is, but we can describe its effects. It acts like a form of anti-gravity, a repulsive force that is woven into the very fabric of space itself. It is a property of the vacuum, where dark matter's gravity pulls galaxies together. Dark energy pushes them apart. And unlike gravity, which gets weaker as objects get farther apart, the effect of dark energy seems to be constant, or perhaps even growing stronger. It is an intrinsic energy of space. So as the universe expands and more space is created, more of this dark energy comes into being. More space means more repulsive push, which means the expansion speeds up, which creates more space and more dark energy in a self-perpetuating runaway cycle. When we take a census of all the matter and energy in the universe, the picture becomes even stranger. We find that this mysterious dark energy accounts for nearly 70% of the total energy content of the cosmos. Dark matter makes up about 25%, and the normal, atomic matter, the stuff of stars, planets, and people, makes up less than 5%. Our entire reality, everything we have ever known or seen or touched, is built upon a tiny sliver of what is actually out there. The universe is not what it seems. It is a dark and accelerating place, governed by substances and forces that lie almost completely beyond our comprehension. This discovery changes everything about our predictions for the ultimate fate of the cosmos. With the expansion accelerating, the universe is not heading for a big crunch. Instead, it seems destined for a big freeze, or heat death. Galaxies will be pushed farther and farther apart at ever-increasing speeds. Eventually, they will be receding from us so fast that their light will never be able to reach us. One by one, the galaxies beyond our local group will disappear from our sky. Our cosmic horizon will shrink. The universe will become a lonely and isolated place. The stars within our own merged galaxy will eventually burn out, and the cosmos will fade into a cold, dark, and silent expanse of dying embers and black holes, drifting ever farther apart in an endless, accelerating darkness. Understanding the nature of dark energy is now one of the greatest challenges in all of physics. It is a mystery that touches upon the fundamental nature of space, the value of the energy of the void, and the ultimate destiny of everything. The universe is not a random scattering of objects. It has a distinct and beautiful and utterly colossal structure. On the very largest scales, galaxies are not distributed uniformly. They are arranged in an intricate and delicate pattern known as the cosmic web. Imagine zooming out, so far out that entire galaxies are just tiny points of light. From this vantage point, you would see that the universe resembles a three-dimensional spider's web, or the intricate structure of a nerve cell. There are vast, long thread-like structures called filaments. These filaments are woven from dark matter, and they are threaded with galaxies, like pearls on a string. They can stretch for hundreds of millions of light years, crisscrossing the cosmos and connecting the great galactic clusters. Where these filaments meet, they form dense, bright knots. These are the superclusters of galaxies, the great cosmic cities, immense congregations of thousands of galaxies, all bound together by their mutual gravity, swirling in a hot bath of intergalactic gas. Our own Milky Way galaxy resides in a smaller group, on the outskirts of the Virgo supercluster. And in between these glowing filaments and dense clusters lie the great voids, vast, almost empty regions of space. These are the silent, dark expanses of the universe. They are roughly spherical and can be tens or even hundreds of millions of light years across. They are not perfectly empty. They contain a few sparse, lonely galaxies and a thin, tenuous whisper of dark matter. But for the most part, they are the great deserts of the cosmos. This beautiful, web-like structure is a direct consequence of those tiny, quantum fluctuations in the early universe, the faint ripples we see in the cosmic microwave background. Gravity, acting over billions of years, amplified those initial, tiny density variations. The slightly denser regions pulled in more and more matter, collapsing to form the filaments and clusters. The slightly less dense regions were left behind, their matter flowing away towards the denser areas, and thus they expanded to become the great voids. The dark matter provided the invisible scaffolding for this structure. It collapsed first, forming the great halos and filaments of the web. Then, the normal, baryonic matter, the gas that would eventually form stars and galaxies, was pulled by gravity into this pre-existing dark matter framework. The gas flowed along the filaments, like rivers flowing into a great sea, funneling into the dense nodes where it would cool and condense and ignite into the galaxies we see today. So when we look out at the universe, we are seeing a delicate, interconnected network, a cosmic ecosystem where galaxies are born and live along these vast, nourishing threads of matter. Their growth, their interactions, and their evolution are all guided by their place within this grand architecture. The cosmic web reveals a universe that is not random, but is shaped by the subtle interplay of gravity, dark matter, and the faint, primordial echoes of its own birth. It is a sprawling and silent network that connects everything across the most unimaginable of distances. And within this vast, luminous web, in a relatively quiet and unassuming filament, lies our own home, a city of stars, our galaxy, the Milky Way. From the outside, if we could drift above its plane, we would see a breathtaking sight. A great, sprawling spiral, 100,000 light years across. At its center is a dense, glowing heart. A bright, elongated bulge of old, golden stars, packed tightly together, orbiting a supermassive black hole that sleeps silently in the core. From this brilliant center, great arms of stars, gas and dust, unfurl in a graceful, cosmic pinwheel. These are the spiral arms, the luminous boulevards of our galactic city. They are traced by the light of brilliant, young blue stars, which are born and die within their confines. The arms are also filled with vast, ethereal clouds of hydrogen gas, which glow with a soft, crimson light, energized by the radiation from these newborn suns. These are the stellar nurseries, the birthplaces of stars. Lacing these glowing arms are dark, intricate lanes of cosmic dust, wispy tendrils of soot and carbon, that obscure the light from behind, creating a beautiful and profound sense of depth and texture. This entire, magnificent structure, this island of 200 to 400 billion stars, is not static. It is in constant and majestic motion. The entire galaxy is rotating, spinning on its axis, in a slow and silent cosmic waltz. And the speed of this rotation is almost impossible to comprehend. Our solar system, located about 2/3 of the way out from the galactic center, in a smaller, secondary arm known as the Orion Spur, is being carried along in this grand rotation at an astonishing speed, over 500,000 miles per hour, or about 220 kilometers every single second. It is a speed so great that if you were traveling that fast in a spaceship, you could circumnavigate the Earth in just a few minutes. Yet, on the scale of the galaxy, this dizzying velocity translates into a slow and graceful journey. The distances are so immense that even at this incredible speed, it takes our Sun and its family of planets roughly 230 to 250 million years to complete just one single orbit around the galactic center. This vast span of time is sometimes called a galactic year or a cosmic year. It is a clock that ticks on a scale we can barely imagine. Our Sun has been in existence for about 4.5 billion years, which means it has only completed this grand circuit about 20 times. We are cosmic infants in a galaxy that has seen countless suns be born and die. Think of what our own planet was like. The last time our solar system was in this same position, in its orbit around the galaxy. 1 galactic year ago, 250 million years in the past. The continents on Earth were merged into the single supercontinent of Pangaea. The first dinosaurs were just beginning to evolve. The great forests of the Carboniferous period had come and gone. The sky was filled with a different pattern of stars, and all the while, our solar system was silently and steadily gliding through the interstellar medium on its long, circular path. This journey is not a simple, clean loop. It is a voyage through the varied landscapes of the galaxy. The spiral arms are not solid, fixed structures. They are more like cosmic traffic jams. They are density waves that move through the galactic disk at a different speed than the stars themselves. So, as we orbit, our solar system passes into and out of these spiral arms. For millions of years, we might drift through the relatively calm and sparse space between the arms. And then, our path will carry us into one of the dense, bustling arms. Here, we pass through the great clouds of gas and dust, the stellar nurseries. We witness, from a safe distance, the brilliant fires of newly forming stars. Our solar system is bathed in the light of young, massive, blue suns. We are closer to the epicenters of cosmic creation. Then, after millions more years, we pass through the arm and emerge once again into the quieter space beyond. And despite this incredible speed, this journey through bustling stellar neighborhoods, the voyage is overwhelmingly peaceful. The reason is the sheer, unimaginable emptiness of space. Even within a galaxy, the distances between stars are so vast that collisions are almost statistically impossible. If our sun were the size of a grapefruit in New York City, its nearest stellar neighbor, Proxima Centauri, would be another grapefruit in San Francisco. The space in between is an immense and profound void. So we are on a grand cosmic journey, carried by the silent, gravitational currents of the Milky Way, racing at 500,000 miles per hour through a silence so deep and an emptiness so vast that the motion feels like perfect stillness. It is a reminder that even in what feels like a moment of quiet repose, we are part of a dynamic and ever-moving universe. A silent and perpetual voyage through a city made of starlight. These great star cities, these galaxies, are not always solitary islands, drifting peacefully in the void. Over the immense timescales of the cosmos, they too are in motion, and their paths sometimes cross. Sometimes galaxies collide. The word collision here is again somewhat misleading. It does not conjure the correct image. This is not a violent, high-speed crash, like two ships colliding at sea. Because of the vast emptiness within galaxies, a galactic collision is a slow and surprisingly graceful affair. A majestic dance that can last for hundreds of millions or even billions of years. It begins as two galaxies, drawn together by their mutual gravitational attraction, begin to approach one another. From a distance, they would look like two beautiful spiral pinwheels, slowly drifting closer. As they get nearer, the powerful forces of gravity begin to take effect. They begin to distort one another. Long, ethereal tendrils of stars and gas, called tidal tails, are pulled out from the edges of each galaxy, stretching for hundreds of thousands of light years into intergalactic space. The elegant spiral structures become warped and chaotic, The two galaxies then pass through each other. And in this first pass, something remarkable happens. Or rather, something remarkable doesn't happen. Despite the two galaxies, with their billions of stars, merging into the same volume of space, it is almost certain that not a single pair of stars will physically collide. The space between the stars is simply too vast. It is like two swarms of bees, interpenetrating each other, without any two bees actually touching. But the gas clouds within the galaxies are a different story. Unlike the stars, these vast, diffuse clouds of hydrogen are immense. They can be dozens of light years across. And when these clouds from the two different galaxies meet, they do collide. They slam into each other, creating massive shockwaves. This collision compresses the gas, triggering a furious, galaxy-wide burst of star formation. For a few million years, the merging galaxies are lit up with the brilliant blue light of millions of newborn stars. They become what are known as starburst galaxies, one of the most luminous and active types of objects in the universe. After this first pass, the galaxies do not escape each other's grasp. Gravity is too strong. They slow down and are pulled back together for a second pass. They will swing around each other, passing through one another again and again in a slow, cosmic embrace. With each pass, their individual structures are further erased. The beautiful spirals dissolve into a chaotic, jumbled mass of stars. Eventually, after perhaps 1 billion years of this gravitational dance, the two galaxies will have fully merged. Their separate identities are lost. They settle down to become a single, larger galaxy. Often, the result of a merger between two large spiral galaxies is a giant elliptical galaxy, a vast, spheroidal swarm of older, golden stars with very little gas and dust left for new star formation. A new and more sedate cosmic city has been born from the union of two others. And the supermassive black holes that once resided at the center of each of the original galaxies also find each other. They spiral inward, towards the center of the newly formed galaxy, and eventually, they too will merge, creating an even larger black hole. This final, violent merger can release a colossal burst of energy in the form of gravitational waves, ripples in the fabric of space-time itself. This process of galactic collision and merger is a fundamental part of how the universe evolves. It is how galaxies grow. And it is part of our own future. Our Milky Way is currently on a collision course with our nearest large neighbor, the Andromeda Galaxy. Andromeda is slightly larger than our own galaxy, and it is hurtling towards us at a speed of about 250 Zarazen miles per hour. There is no need for immediate concern. The collision will not begin for about 4.5 billion years. But it is destined to happen. In the far future, the night sky of a future Earth will be a spectacular sight. Andromeda will grow larger and larger until it fills the entire horizon. Then, our two galaxies will begin their long, slow dance. Tidal tails will be thrown out, and a great burst of star formation will light up the cosmos. Our solar system will likely be thrown into a new, much wider orbit within the new, merged galaxy. But it is unlikely to be destroyed. Eventually, the two will settle into a single, giant elliptical galaxy, which some astronomers have already nicknamed Milkomeda. It is a beautiful and poignant reminder that even on the grandest of scales, the universe is a place of constant change, of interaction, and of slow, majestic, and creative transformation. in the distant universe. Billions of light years away from us, we can see objects of almost unimaginable power and brilliance. They are the lighthouses of the cosmos. Objects so luminous, they can outshine their entire host galaxy 100 times over. They are called quasars. The name quasar is a contraction of quasi, stellar radio source, which hints at their history. When they were first discovered in the 1950s and 60s, they appeared in radio telescopes as powerful, point-like sources of radio waves. But when astronomers looked for them with optical telescopes, they just saw faint, star-like points of light. They were a deep mystery. They looked like stars, but their light signatures, their spectra, were unlike anything ever seen before. The breakthrough came when astronomer Martin Schmidt realized that the bizarre spectral lines of one of the brightest quasars, 3C273, were actually the familiar lines of hydrogen. But they were shifted towards the red end of the spectrum by an enormous amount. This massive redshift meant that the quasar was not a nearby star at all. It was incredibly distant, billions of light years away. And if it was that far away, and still appeared as a bright point of light in our telescopes, its true, intrinsic luminosity had to be absolutely staggering. It was generating more energy than 1 trillion suns, all from a region of space not much larger than our solar system. What could possibly be powerful enough to generate such an incredible amount of light? The answer lies at the very heart of a young, active galaxy. The engine of a quasar is a supermassive black hole, not a quiet, sleeping one like the one in the center of our Milky Way today, but a ravenous one. A black hole that is actively and voraciously consuming enormous amounts of matter. In the early universe, galaxies were often much richer in gas than they are today. And this gas, in the chaotic environment of a young galaxy, can be funneled down towards the central black hole. But the matter doesn't fall straight in. Because of its own momentum, it spirals inward, forming a vast, flat, spinning structure called an accretion disk. This disk is a place of incredible violence and energy. As the gas spirals closer and closer to the black hole, it moves at tremendous speeds, approaching the speed of light. The friction between different layers of gas in the disk and the immense tidal forces from the black hole's gravity heat the matter to unimaginable temperatures, millions or even billions of degrees. The matter in the accretion disk glows with an intensity that is difficult to fathom. It shines brightly across the entire electromagnetic spectrum, from radio waves to visible light to powerful X-rays and gamma rays. This is the light of a quasar. It is not light from the black hole itself, from which nothing can escape. It is the light from the matter being heated to incandescence in its final, desperate spiral before it crosses the event horizon and is lost from our universe forever. A quasar is the death scream of matter, transformed into the brightest light in the cosmos. Quasars are phenomena of the young universe. Because they are so incredibly distant, we are seeing them as they were billions of years ago. They represent a phase in the life of many galaxies, a wild and energetic youth. As the galaxy matures, the central black hole consumes all the readily available gas in its vicinity. The accretion disk thins out, and the quasar's light fades. The galaxy settles down into a quieter, more sedate middle age, like our own Milky Way. The monster at its heart goes to sleep. So quasars are not just fascinating objects in their own right. They are powerful tools for studying the early universe. Because their light is so brilliant, it acts like a cosmic searchlight. As the quasar's light travels towards us for billions of years, it passes through the vast, intervening clouds of intergalactic gas, the faint, tenuous material that lies in the great voids between galaxies. The atoms in these clouds absorb the quasar's light at very specific frequencies, leaving a dark, barcode-like pattern of absorption lines in its spectrum. By studying this forest of absorption lines, astronomers can learn an incredible amount about the otherwise invisible material that fills the cosmos. They can map the distribution of matter, measure its temperature and density, and even determine its chemical composition. At different points in cosmic history, the quasars serve as cosmic lighthouses, illuminating the dark and unseen structures of the universe's youth, and allowing us to piece together the story of how the cosmos evolved, from its smooth, simple beginnings to the complex, web-like structure we see today. The birth of our universe, the Big Bang, set in motion the expansion of space-time. But in the very, very first moments of its existence, in a sliver of time, so short it defies our intuition, the universe may have experienced an even more extraordinary and violent phase of growth, a period of hyper-expansion known as cosmic inflation. The theory of inflation was proposed to solve some deep puzzles in cosmology. One of these is the horizon problem. When we look at the cosmic microwave background radiation, we see that it is almost perfectly uniform in temperature. In every direction we look, patches of the sky on opposite sides of the universe are at the same temperature, to within 1 part in 100,000. In the standard Big Bang model, this is a profound mystery. These two opposite regions of the sky are separated by 27 billion light years today. When the CMB light was emitted, they were still millions of light years apart. And the universe was only 380,000 years old. There has not been enough time in the history of the universe for light, or any signal, to travel from one region to the other. They could never have been in causal contact. They could never have exchanged heat or information to even out their temperatures. So how did they know to be at the exact same temperature? It's like finding two people on opposite sides of the Earth who have never met or communicated, but who have independently chosen to wear the exact same outfit, down to the last detail. It seems impossibly coincidental. Cosmic inflation offers a solution. It proposes that in the first fraction of a second after the Big Bang, from about 10 to the minus 36 seconds to 10 to the minus 32 seconds, a tremendous amount of energy, locked in a quantum field called the inflaton field, caused the fabric of space itself to expand at a truly explosive, exponential rate. During this infinitesimal instant, the universe is thought to have doubled in size, at least 100 times over. A region of space, far smaller than a proton, was stretched to become a region larger than our entire observable universe today. This expansion was not just fast. It was faster than the speed of light. Now, this does not violate Einstein's theory of relativity. Relativity states that no object can travel through space faster than light. But it places no limit on how fast space itself can expand. Space is not a thing. It is a dynamic, geometric stage. This incredible hyper-fast expansion solves the horizon problem. Before inflation began, the entire region that would become our observable universe was a tiny, subatomic patch of space. It was so small that all of its parts were in close causal contact. They had plenty of time to interact and reach a uniform temperature. Then, inflation suddenly grabbed this tiny, smooth, and uniform region and stretched it to cosmic proportions. The uniformity we see in the CMB today is the memory of the uniformity that existed in that single, tiny, primordial patch. Inflation also explains another cosmic mystery: why the universe is so geometrically flat. According to general relativity, space-time can have a curvature. It can be positively curved, like the surface of a sphere, or negatively curved, like the surface of a saddle. Or it can be flat, like a sheet of paper. Our measurements show that our universe is incredibly close to being perfectly flat. This is also a highly unlikely coincidence in the standard Big Bang model. Any tiny deviation from perfect flatness in the beginning would have been magnified over 13.8 billion years of expansion to create a universe that is wildly curved today. Inflation explains this with a simple analogy. Imagine the surface of a small, crumpled ball. It is clearly very curved. But if you inflate that ball to the size of the Earth, any small patch on its surface will now appear to be perfectly flat. This is what inflation did to the geometry of spacetime. It took the initial, potentially curved universe and stretched it out so much that our observable patch of it now appears to be perfectly flat. And perhaps most profoundly, inflation provides the seeds for all the structure we see in the cosmos. In the quantum world, the world of the very small, there is a constant, unavoidable bubbling of energy, tiny spontaneous and random fluctuations in the quantum fields. This is quantum foam. During the period of inflation, these microscopic, quantum fluctuations were stretched along with space itself. They were magnified from subatomic scales to astrophysical scales. These stretched out quantum jitters became the tiny, macroscopic density variations that were imprinted upon the universe. These are the very same ripples we see in the cosmic microwave background. The seeds from which all the galaxies and all the great structures of the cosmic web would eventually grow. So the largest structures in our universe may have their origins in the smallest and most fleeting of quantum events. A beautiful and profound connection between the unimaginably large and the unimaginably small. For a long time after the Big Bang, even after the universe became transparent, the cosmos was a dark and silent place. The great cosmic dark ages. The universe was filled with a vast and mostly uniform ocean of neutral hydrogen and helium gas. There was light, the fading afterglow of the cosmic microwave background, but it was a cold, dim, and ever reddening light. There were no stars, no galaxies, no sources of new light. The universe was a place of profound and patient darkness. This dark era lasted for hundreds of millions of years. But during this long twilight, gravity was slowly and silently at work. In the regions where inflation had sown the seeds of slightly higher density, the dark matter began to clump together, forming the first small, gravitational halos. And the normal matter, the hydrogen and helium gas, was drawn into the centers of these dark matter halos. As the gas fell inward, it became more and more compressed. The pressure and temperature at the centers of these primordial clouds began to rise. Eventually, after perhaps 200 million years of slow, gravitational collapse, the core of the densest clouds, reached a critical temperature of about 10 million degrees. At this point, the nuclear furnace ignited. Hydrogen atoms began to fuse into helium. A star was born. These were the first stars in the universe. Astronomers call them population key stars. And they were unlike any stars that exist today. They were formed from the pure, pristine gas of the early universe, almost entirely hydrogen and helium. They contained none of the heavier elements, the metals, that were forged in later generations of stars. And because of this simple chemical makeup, the physics of their formation was different. They are thought to have been colossal monsters, hundreds of times more massive than our own sun. And because they were so massive, they were also incredibly hot and incredibly luminous. They burned with a brilliant, blue, white light and lived for only a very short time. Perhaps just a few million years. But in their brief and spectacular lives, they changed the universe forever. Their intense, high-energy ultraviolet radiation blasted out into the surrounding, neutral hydrogen gas. This radiation was powerful enough to strip the electrons off the hydrogen atoms, a process called reionization. One by one, these first stars and the first small galaxies they began to form created growing bubbles of ionized, transparent plasma around them. Slowly, over hundreds of millions of years, these individual bubbles grew and merged until the entire universe had been transformed. The cosmic fog was lifted for good. The Dark Ages came to an end, and the era of light, the cosmic dawn, had begun. The first stars were not just agents of reionization. They were also the first cosmic forges. In their incredibly hot cores, they fused hydrogen and helium into the first batches of heavier elements: carbon, oxygen, nitrogen, silicon, iron. The very elements that are essential for the formation of rocky planets and for the chemistry of life. When these massive first stars reached the end of their short lives, they did not fade away gently. They exploded as magnificent supernovae. These explosions scattered the newly forged heavy elements out into interstellar space. This enriched the surrounding gas clouds. So the next generation of stars, population stars, would be born from a slightly less pristine and more chemically complex material. And so the cycle continued. Each generation of stars lived and died and seeded the cosmos with ever heavier elements. Our own sun is a population I star, a relatively recent third-generation star. It is rich in these heavy elements, these metals. And it is this metallic richness that made the formation of our solar system, with its rocky planets like Earth, even possible. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in the heart of a massive star long ago. A star that lived and died and scattered its ashes across the galaxy to provide the raw materials for new suns, new worlds, and new life. We are, in the most literal sense, made of stardust. And our story begins with those first, brilliant, and lonely points of light that pierced the long, cosmic darkness and lit up the universe for the very first time. The universe is not just filled with light. It is also constantly being traversed by invisible messengers, high-energy particles that race through the vast emptiness of space at speeds approaching that of light itself. These are the cosmic rays. Unlike light, which is made of massless photons, cosmic rays are actual pieces of matter. Most of them, about 90%, are protons, the bare nuclei of hydrogen atoms. A smaller fraction are the nuclei of helium atoms, and an even smaller percentage are the nuclei of heavier elements. There is also a component of electrons and other subatomic particles. They are a rain of matter, a constant subatomic drizzle, falling upon our world from the depths of space, and they are incredibly energetic. The particles in a gentle breeze have a certain kinetic energy. The particles in a speeding bullet have much more. But the kinetic energy of a single high-energy cosmic ray particle can be millions or even billions of times greater than the energy of particles accelerated in our most powerful particle accelerators on Earth, like the Large Hadron Collider. A single subatomic proton can hit our atmosphere with the kinetic energy of a well-thrown baseball. The question is, what in the universe can act as such a powerful, natural particle accelerator? The answer, for most of the cosmic rays that reach us, lies in the violent death of massive stars. Supernova explosions. When a giant star explodes, it sends a colossal shockwave, blasting out into the surrounding interstellar medium. This shockwave is a moving wall of superheated gas and magnetic fields. As charged particles, like protons, get caught up in this turbulent environment, they can be bounced back and forth across the shock front, again and again, like a cosmic ping-pong ball. With each bounce, they gain more and more energy, accelerated by the powerful, chaotic magnetic fields. Eventually, after thousands of these interactions, they gain so much energy that they escape the supernova remnant entirely and are flung out into the galaxy as a high-energy cosmic ray. They then begin a long and meandering journey. The galaxy is threaded with weak but vast magnetic fields. And because cosmic rays are charged particles, their paths are bent and deflected by these fields. They do not travel in straight lines. They spiral and loop and wander on a chaotic, random walk through the Milky Way. This is why we cannot trace them back to their specific source. By the time they reach Earth, they are coming at us from all directions, a uniform, isotropic shower. Their journey may have lasted for millions of years, carrying them across tens of thousands of light years from the site of an ancient, long-faded stellar explosion. The most energetic cosmic rays, the ultra high energy, ones with the power of a baseball, are an even deeper mystery. A supernova shockwave is not powerful enough to create them. Their origins must lie in even more extreme and violent cosmic events. Perhaps they are born in the powerful jets of material, blasted out from the accretion disks of supermassive black holes at the centers of active galaxies. Or perhaps they are created in the cataclysmic merger of two neutron stars. These are the most energetic phenomena we know of in the universe, and they are the leading candidates for these most extreme of cosmic messengers. When a cosmic ray finally ends its long journey, by striking the Earth's atmosphere, it does so with tremendous force. It collides with the nucleus of a nitrogen or oxygen atom about 10 to 20 kilometers up. This collision shatters the atmospheric nucleus and creates a cascade of new, secondary particles. Pions, muons, neutrinos. These new particles then fly onward and collide with other atmospheric atoms, creating yet more particles. The result is a vast, cone-shaped shower of millions of particles, all raining down through the atmosphere. This is called an extensive air shower. By the time the shower reaches the ground, it can be spread out over several square kilometers. Specialized observatories, with arrays of detectors spread out over vast areas of land, are designed to catch these showers and reconstruct the energy and direction of the original, primary cosmic ray particle. And these visitors from deep space have a tangible effect on our world. They can cause soft errors in our electronic devices, flipping a bit in a computer's memory. They are a significant source of radiation exposure for airline crews and frequent flyers, who spend a lot of time in the thinner, upper atmosphere. And, over geological timescales, they have been a subtle but persistent driver of mutation in the DNA of living organisms, a small but constant cosmic pressure on the course of evolution. Though invisible and silent, cosmic rays are a fundamental link between our planet and the most powerful and violent events in the wider universe. They are tangible pieces of distant stars and galaxies delivered to our doorstep, a constant reminder that we live in a dynamic and energetic cosmos, and that the quiet emptiness of space is filled with silent and incredibly fast-moving travelers. Our galaxy, the Milky Way, is not alone. It is part of a local cosmic community, a small, gravitationally bound collection of galaxies known simply as the local group. The local group is a relatively modest cluster. It is dominated by its two largest members, our own Milky Way and the Andromeda Galaxy. These are the two great matriarchs of our neighborhood, two massive, beautiful spirals. The rest of the group is composed of dozens of smaller, dwarf galaxies. Some are smaller, irregular spirals. Others are faint, diffuse spheroidal blobs of stars. Many of these little dwarf galaxies are in orbit around the two giants. They are our galactic satellites, our celestial moons. The most famous of these are the large and small Magellanic Clouds, which are visible to the naked eye from the southern hemisphere, looking like two faint, detached pieces of the Milky Way. But this local group is itself just one small part of a much, much larger structure. Our entire local group is just one suburb in an immense cosmic metropolis, a supercluster of galaxies. This structure is called Laniakea. The name Laniakea is from the Hawaiian language, and it means immeasurable heaven. It is a beautiful and fitting name for a structure of such incomprehensible scale. Laniakea contains roughly 100,000 galaxies, and it stretches for over 500 million light years from end to end. It is one of the largest known structures in the universe. Laniakea is not a simple, spherical cluster. It is a sprawling, filamentary network. The galaxies within it are not moving randomly. They are flowing. Just as individual raindrops on a window pane will flow together to form larger streams and rivers, the galaxies in our cosmic neighborhood are all flowing along gravitational currents. They are moving along the great filaments of the cosmic web. Astronomers were able to define the boundaries of Laniakea, not by just mapping the positions of galaxies, but by mapping their motions. They carefully measured the velocities of thousands of galaxies and subtracted the component of their motion that was due to the overall expansion of the universe. What was left was the peculiar velocity, the motion caused by the local gravitational pulls of neighboring structures. When they mapped these peculiar velocities, they saw a remarkable pattern. They saw great flows and currents of galaxies, and they could trace these flows to a central basin of attraction. At the heart of Laniakea is a region of immense gravitational influence, known as the Great Attractor. We cannot see this region clearly in visible light because it lies in a direction that is obscured by the dense dust and stars of our own Milky Way's disk, a region called the zone of avoidance. But we can detect its enormous mass by its gravitational pull. The Great Attractor is a massive supercluster of galaxies, and it is pulling our local group and thousands of other galaxies towards it. Our Milky Way is currently moving towards this region at a speed of over 1 million miles per hour. So Laniakea is defined as the entire collection of galaxies that are all flowing inward towards this common gravitational center. It is a cosmic watershed, and our local group lies on one of its outer tributaries. This discovery has changed our cosmic address. We live on planet Earth, in the solar system. The solar system is in the Orion spur of the Milky Way galaxy. The Milky Way is one of the two dominant members of the local group. And the local group is a small, outlying province of the Great Laniakea supercluster. It gives us a profound sense of place and of motion. We are not just sitting still. We are spinning on the Earth's axis. We are orbiting the Sun. Our solar system is orbiting the center of the Milky Way, and our entire Milky Way galaxy is on a grand, gravitational pilgrimage, flowing along a cosmic river of galaxies, across hundreds of millions of light years, towards the unseen and mysterious heart of our home supercluster. Just as the continents on Earth are separated by vast oceans, the great filaments and clusters of the cosmic web are separated by even vaster regions of emptiness, the great cosmic voids. These are the most dense, and seemingly desolate regions of the universe, while the filaments are the bustling highways and cities of the cosmos. The voids are the immense, silent countryside. They are colossal, roughly spherical bubbles of space that can span tens or even hundreds of millions of light years in diameter. The space inside them is not a perfect vacuum, but it is incredibly sparse. The density of matter inside a void is typically less than 1/10 of the average density of the universe. These voids were born from the same primordial, quantum fluctuations as the clusters and filaments. They originated from the regions in the early universe that were just slightly less dense than average. As gravity pulled matter towards the denser regions to form the filaments, it simultaneously pulled matter out of these dense regions. They became the cosmic basins from which the matter was drained. So as the filaments grew richer, the voids grew emptier. Studying these voids is just as important for understanding the universe as studying the galaxies themselves. They are a pristine laboratory for cosmology. Because they are so empty, the gentle, repulsive push of dark energy is the dominant force within them. Gravity's influence is much weaker. By studying the subtle motions of the few galaxies that do exist inside or on the edges of voids, and by observing how the voids themselves grow and evolve over time, astronomers can make some of the most precise measurements of the effects of dark energy and test our fundamental understanding of gravity on the largest scales. The light from distant galaxies must also travel through these great voids to reach us, and as it does, it is subtly affected. A phenomenon known as the integrated Sachs-Wolf effect predicts that photons gain a tiny amount of energy, a blue shift, as they fall into the shallow gravitational well of a large structure like a supercluster. and then lose that same amount of energy, a redshift, as they climb back out. But in a universe with dark energy, this is not a perfect cancellation. By the time the photon is climbing out of the well, the structure has been stretched slightly larger by cosmic acceleration. So the photon doesn't lose quite as much energy as it gained. The effect is reversed for voids. Light passing through a void should be just a tiny bit colder, or more redshifted. By looking for these subtle cold and hot spots in the cosmic microwave background that line up with known voids and superclusters, scientists can directly map the influence of dark energy on the structure of the cosmos. And while they seem empty, the voids may harbor secrets. The few galaxies that exist within them are fascinating objects. They are often smaller and bluer and less disturbed than galaxies in dense environments. They have been evolving in quiet isolation, far from the violent mergers and interactions that are common in clusters. They are like pristine, cosmic fossils that can give us a glimpse of what galaxies might have looked like before the rough and tumble life of a galactic city. The voids carve out the shape of the cosmic web. They define the boundaries of the great filaments. They are the silent, dark counterpoint to the bright, luminous structures of the universe. They are a profound reminder of the power of emptiness and of the delicate balance between matter and the void that shapes the entire, grand architecture of the cosmos. They are the deep, quiet breaths of space that give the universe its texture and its form. Flowing through the cosmos, passing through us at every moment, is a constant, silent rain of ghostly particles. They are born in the fiery hearts of stars, in the cataclysmic explosions of supernovae, and in the violent collisions of cosmic rays with our atmosphere. They are neutrinos. Neutrinos are among the most abundant and most enigmatic of all the fundamental particles in the universe. They are often called ghost particles, and for good reason. They are almost massless. For a long time, they were thought to have no mass at all. We now know they have a tiny, but non-zero mass, though we have yet to measure it precisely. And they have no electric charge. This combination of properties means that they interact with other matter extremely weakly. To a neutrino, solid matter is almost entirely empty space, while a photon of light will be stopped by a sheet of paper, and a proton will be stopped by your skin. A typical neutrino can pass through an entire light year of solid lead without ever hitting anything. It simply doesn't feel the presence of other particles. It interacts only through the weak nuclear force and, to a much lesser extent, gravity. And the weak force, as its name suggests, is incredibly feeble and acts only over incredibly short distances. This elusiveness is difficult to overstate. Right now, as you are here, trillions of neutrinos are passing through your body every single second. Most of these are coming from the sun. The nuclear fusion reactions in the sun's core that produce the light and heat that sustain our world also produce a colossal flood of neutrinos. This flood streams out of the sun and washes over the Earth. They pass through the entire planet, from one side to the other, as if it were a pane of glass. They pass through you, and you feel absolutely nothing. In your entire lifetime, it is probable that only a handful of these solar neutrinos will ever interact with a single atom in your body. Because they are so difficult to catch, detecting them requires extraordinary measures. neutrino observatories are some of the most remarkable scientific instruments ever built. They are not like traditional telescopes that look up at the sky. Instead, they are built deep underground, in old mines or in tunnels bored into mountains. This is to shield them from the constant rain of other, more interactive particles, like cosmic ray muons, that would otherwise overwhelm their sensitive detectors. One famous type of neutrino detector, like the Super Kamiokund in Japan, consists of a gigantic tank filled with thousands of tons of ultra-pure water. Lining the walls of this vast, dark cavern are thousands of incredibly sensitive light detectors called photomultiplier tubes. The experimenters then wait, patiently, for the 1 in a trillion chance that a passing neutrino will, by pure random luck, strike the nucleus of an atom in the water molecule. When this rare interaction does happen, it can knock an electron loose and send it flying off through the water at a speed faster than the speed of light in water. Nothing can travel faster than the speed of light in a vacuum, but light slows down when it passes through a medium like water, so it's possible for a particle to outpace it. When a particle does this, it produces a faint, conical flash of blue light, called Cherenkov radiation. It is the optical equivalent of a sonic boom. The photomultiplier tubes detect this tiny flash of light, and by analyzing its shape and timing, scientists can reconstruct the energy and direction of the original neutrino. By studying these ghostly messengers, we can learn things about the universe that are otherwise impossible to know. Because neutrinos stream directly out of the sun's core, unimpeded. They give us a direct window into the nuclear furnace at the heart of our star. The light we see from the sun's surface, the photons, took 100,000 years to randomly walk their way out of the core. But the neutrinos make the journey in just over 8 minutes. They are giving us a real-time report on the state of the sun's fusion reactions. Neutrinos are also produced in the core collapse of a massive star, just before it goes supernova. In fact, in the final, violent moments of a star's life, the vast majority of its gravitational collapse energy is released not as light, but as a titanic burst of neutrinos. When supernova 1987A exploded in the Large Magellanic Cloud, neutrino detectors on Earth saw a burst of a few dozen neutrinos, about 3 hours before the first light from the explosion arrived. Those ghostly particles were the first heralds of the star's death, and they provided an invaluable confirmation of our theories of stellar collapse. They are silent, invisible, and almost intangible, but neutrinos are a unique and powerful tool that connect us to the most secret and energetic processes in the entire cosmos. When we look out at the universe, on the very, very largest of scales, something remarkable becomes apparent. The universe appears to be surprisingly uniform. It looks much the same everywhere and in every direction. This idea is so fundamental to our understanding of the cosmos that it has a name, the cosmological principle. The cosmological principle is made of 2 parts. The first is homogeneity. This is the idea that, on large enough scales, the universe is the same everywhere. Of course, this is not true on small scales. We live on a dense planet in a relatively empty solar system. Our solar system is in a dense galaxy, which is surrounded by the vast emptiness of intergalactic space. The universe is clearly very lumpy. But if you zoom out far enough, to scales of hundreds of millions of light years, these lumps and voids begin to average out. If you were to take a very large, imaginary box, say 1 billion light-years on a side, and place it anywhere in the universe, it would contain roughly the same amount of matter, the same number of galaxies, and the same large scale structure as a similar box placed anywhere else. Statistically, there are no special places in the universe. The second part of the principle is isotropy. This is the idea that the universe looks the same in every direction. Again, this is not true on small scales. If we look in one direction, we see the dense band of the Milky Way. In another, we see the Andromeda Galaxy. In another, the empty blackness of a local void. But again, if we average our view over very large angles, the universe appears uniform. There is no preferred direction. We see roughly the same number of galaxies, with the same properties, no matter which way we point our telescopes. There is no cosmic up or down, no celestial North Pole. The most powerful evidence for this principle comes from the cosmic microwave background radiation. The CMB is a snapshot of the entire universe at a very early time, and it is incredibly isotropic. The temperature of this ancient light is the same to within 1 part in 100,000, no matter which direction in the sky we measure. This astonishing uniformity tells us that the early universe itself was incredibly smooth and well mixed. The cosmological principle is a profoundly important idea. It is, in some ways, a statement of cosmic humility. It is the ultimate extension of the Copernican idea that the Earth is not the center of the universe. The cosmological principle goes further. It says that nothing is the center of the universe. Our galaxy is not special. Our supercluster is not special. Every place and every observer has an equally valid and non-privileged view of the cosmos. This principle is also a tremendously powerful tool for scientists. Because if we assume the universe is the same everywhere, it means that the laws of physics that we discover here on Earth should be the same everywhere. The properties of gravity, of light, of atoms should be universal. This allows us to build mathematical models of the entire universe, based on the physics we can test in our own laboratories. It makes the science of cosmology possible. Without this assumption, every distant galaxy could be operating under its own unique set of physical laws, and we would have no hope of understanding the cosmos as a coherent whole. So, while the universe is filled with an incredible diversity of beautiful and complex structures, from stars and planets to galaxies and voids, underlying all of this intricate detail is a deep and simple and profound symmetry. A grand, large-scale uniformity that speaks to a common origin, and a shared set of physical laws that govern the entire, magnificent expanse of reality. Just as the universe is filled with a background of ancient light. The cosmic microwave background, our cosmological models predict that it should also be filled with a background of ancient neutrinos. A sea of relic particles from the very first second of the universe's existence. This is the cosmic neutrino background. To understand its origin, we must go back to the primordial furnace of the very early universe. In the first second after the Big Bang, the cosmos was an unimaginably hot and dense soup of fundamental particles. Protons, neutrons, electrons, photons, and neutrinos were all constantly colliding and interacting with each other in a state of thermal equilibrium. They were all part of the same, seething, chaotic plasma. but the universe was expanding and cooling with incredible speed. And as the temperature dropped, the interactions between neutrinos and the other particles became less and less frequent. Neutrinos interact via the weak nuclear force, and the strength of this force is highly dependent on energy. At the extreme energies of the early universe, it was strong enough to keep the neutrinos coupled to the rest of the plasma. But as the universe cooled, the weak force became, well, weaker. At about 1 second after the Big Bang, the universe had cooled to a point where the neutrinos' interactions became so infrequent that they effectively stopped altogether. They decoupled from the rest of the cosmic soup. From this moment on, they have been streaming freely through the expanding universe, almost completely undisturbed. This is a very similar story to the cosmic microwave background, but it happened much, much earlier. The photons of the CMB decoupled from matter at 380,000 years. The neutrinos of the cosmic neutrino background decoupled at just 1 second. This means that these relic neutrinos are messengers from a much earlier and much more extreme epoch of cosmic history. They are a window into the universe when it was a furnace of unimaginable temperature and density. Like the photons of the CMB, these neutrinos have been cooled by the expansion of the universe. They started out with incredibly high energies, but the stretching of spacetime has sapped their momentum. Today, they should have a temperature of about 1.9 degrees above absolute zero, making them even colder than the CMB, and they should be all around us. Cosmological models predict that there should be, on average, about 340 of these relic neutrinos in every single cubic centimeter of space throughout the entire universe. The existence of this background is a firm prediction of the Big Bang model. And while we have not yet detected it directly, we have powerful, indirect evidence that it is there. The presence of this vast number of neutrinos in the early universe had a subtle but measurable effect on the processes of primordial nucleosynthesis, the formation of the first light elements. It also had an effect on the fluctuations in the cosmic microwave background. The observed abundances of helium and deuterium in the universe, and the detailed pattern of ripples in the CMB, both match the predictions of models that include this relic neutrino background almost perfectly. If the CMB wasn't there, our universe would look subtly but noticeably different. But detecting these ancient neutrinos directly is one of the great, and perhaps impossible, challenges of experimental physics. Because they have been cooled so much by cosmic expansion, their energies are now incredibly low. Far, far lower than the energies of neutrinos from the Sun or supernovae. This makes them almost impossibly difficult to detect. The probability of one of these relic neutrinos interacting with an atom in a detector is vanishingly small. We may never be able to build an instrument sensitive enough to see them, but they are there. A silent, invisible sea of particles that fills every corner of the cosmos. A ghostly echo of the first second of creation. They are a testament to the extreme conditions of our universe's birth, and a constant, unseen presence that subtly shapes the evolution of the cosmos and carries the oldest secrets from the very dawn of time. The relentless expansion of the universe, this fundamental stretching of space-time itself, is a concept that has been woven through our journey tonight. But how do we measure it? How can we put a number on the rate at which the entire cosmos is growing. This cosmic speedometer reading is one of the most important numbers in all of cosmology. It is called the Hubble constant. The Hubble constant, named after the pioneering astronomer Edwin Hubble, describes a simple and profound relationship. The farther away a galaxy is from us, the faster it appears to be moving away from us. The constant is the value that links these two quantities. It is usually expressed in a slightly strange unit, kilometers per second per megaparsec. A megaparsec is a unit of distance equal to about 3.26 million light years. So, if the Hubble constant were, for example, 70 kilometers per second per megaparsec, it would mean that for every megaparsec of distance a galaxy is from us, its speed away from us increases by 70 kilometers per second. A galaxy at 1 megaparsec would be receding at 70 kilometers. A galaxy at 10 megaparsecs would be receding at 700 kilometers. Knowing the precise value of the Hubble constant is incredibly important, because it tells us the current expansion rate of the universe. It allows us to work backwards and calculate the age of the universe. A faster expansion rate implies a younger universe, and a slower rate implies an older one. It is a fundamental parameter that underpins our entire cosmological model. It helps us understand the size of the observable universe, its history, and its ultimate fate. But measuring this number with high precision has proven to be one of the most difficult and contentious challenges in modern astronomy. The problem is that there are two main, independent ways to determine the Hubble constant, and frustratingly, they give slightly, but significantly, different answers. The first method is to look at the local universe. This is the approach that Edwin Hubble himself pioneered. It involves measuring the distances to nearby galaxies and then measuring their recession velocities. Measuring the velocity is relatively easy. We can do this by looking at the redshift of a galaxy's light. But measuring the distance is extremely difficult. This is where the cosmic distance ladder comes in. Astronomers start by measuring the distances to the very nearest stars in our own galaxy, using a direct, geometric method called parallax. This is like holding your finger out and looking at it with one eye, then the other, and seeing how it appears to shift against the background. By measuring this tiny shift for a star, as the Earth moves from one side of its orbit to the other, we can calculate its distance. This first rung of the ladder is very accurate, but it only works for relatively nearby stars. Then, for the next rung, astronomers find special types of pulsating stars, called Cepheid variables, in those same nearby regions where we have good parallax distances. They discover a tight relationship between how fast these stars pulsate and their true, intrinsic brightness. Once this relationship is calibrated, they can look for Cepheid variables in more distant galaxies. By measuring their pulsation period, they can determine their true brightness. And by comparing that to how dim they appear, they can calculate the distance to that galaxy. For the final rung of the ladder, they look for those incredibly bright and reliable standard candles, the type Ia supernovae. They find these supernovae exploding in the same, more distant galaxies where they have already found Cepheids. This allows them to calibrate the true brightness of the supernovae. And because supernovae are so incredibly bright, they can be seen in galaxies that are billions of light years away. They allow us to extend our distance measurements deep into the cosmos. When astronomers use this intricate, step-by-step ladder method to measure the distances and velocities of many galaxies, they consistently arrive at a value for the Hubble constant of about 73 kilometers per second per megaparsec. The second method is completely different. It looks at the early universe. This method uses the incredibly detailed map of the cosmic microwave background radiation. The CMB contains a wealth of information about the conditions in the universe when it was just 380,000 years old. The pattern of hot and cold spots in the CMB is a direct result of the physics of the primordial plasma. By feeding all of our knowledge of physics, of gravity, of the behavior of matter and radiation into what is called the standard cosmological model, scientists can create a theoretical model of the CMB. This model has several tunable parameters, including the density of dark matter, the density of dark energy, and the expansion rate of the universe. They then adjust these parameters until their theoretical model of the CMB provides a perfect match to the CMB that we actually observe with our telescopes, like the Planck satellite. When they do this, they can determine all of the universe's key parameters with astonishing precision. And this method gives a value for the Hubble constant of about 67 kilometers per second per megaparsec. And this is the problem: 73 and 67. These two numbers are different, and the measurement uncertainties for both methods are now so small that this difference is statistically significant. It is not just a random error. It appears to be a real physical discrepancy. It has been dubbed the Hubble tension. It is one of the biggest mysteries in cosmology today. It could be that there is some subtle, unknown error in one of the rungs of the cosmic distance ladder. Perhaps our understanding of Cepheid variable stars, or supernova, is incomplete. Or it could be that our standard cosmological model is missing something. Perhaps there was some new, undiscovered type of particle or energy in the early universe that has affected the expansion rate in a way we don't yet understand. Perhaps the nature of dark energy is more complex than we thought. Whatever the answer, this tension is a tantalizing clue. In science, it is often in these small, persistent discrepancies that the seeds of a new revolution in understanding are found. The Hubble tension is a whisper from the cosmos that there is still some deep and fundamental truth about the nature of our expanding universe that we have yet to discover. The light from distant galaxies, as it travels across the expanding universe, carries a fundamental signature of that expansion. Its wavelength is stretched. It is shifted towards the red end of the spectrum. This phenomenon, known as cosmological redshift, is the primary tool we use to map the cosmos and understand its history. It is helpful to distinguish this from the more familiar Doppler effect. The Doppler effect is what happens to sound waves when a source is moving towards or away from you. An ambulance siren sounds higher in pitch as it approaches, and lower in pitch as it moves away. This is because the sound waves are being compressed or stretched out by the motion of the source through the medium of the air. Light waves do the same thing. An object moving towards us through space will have its light waves slightly compressed, a blue shift. An object moving away from us will have its light waves stretched, a redshift. But the redshift we see from distant galaxies is something different and more profound. while the galaxies do have some small, local motion through space. The dominant component of their redshift is not caused by them moving through space at all. It is caused by the fact that space itself is expanding, while the light is in transit. Imagine a single photon of light as a tiny, oscillating wave. It is emitted from a very distant galaxy, billions of years ago. At that moment, it has a certain wavelength. It then begins its long journey towards us. But while it is traveling, the universe is expanding. The fabric of space-time that the photon is traveling through is being stretched. And the light wave is stretched along with it. Its wavelength gets longer and longer. By the time it finally arrives at our telescope, billions of years later, its wavelength is much longer than it was when it started. Blue light becomes red, visible light becomes infrared. The light has been redshifted by the expansion of the cosmos. The amount of redshift is a direct measure of how much the universe has expanded since the light was emitted. If we see a galaxy with a redshift that tells us its light has been stretched to twice its original wavelength, it means that the universe is now twice as large as it was when that light began its journey. This makes redshift an incredibly powerful cosmic tool. It is, in effect, a time machine. By measuring the redshift of a galaxy, we can immediately know how far back in time we are looking. The higher the redshift, the more the universe has expanded, the longer the light has been traveling, and the farther back into the past we are seeing. The faint smudges of the very first galaxies to form have redshifts of 10 or 11 or even higher. This means the light from them has been stretched by a factor of 11 or 12. We are seeing them as they were when the universe was just a tiny fraction of its current size. By collecting the light from thousands and millions of galaxies and carefully measuring their redshifts, astronomers can build up a three-dimensional map of the universe. The 2 dimensions on the sky give us the galaxy's position, and its redshift gives us its distance and its place in cosmic time. It is through these vast redshift surveys that we have been able to map the great filaments and voids of the cosmic web and piece together the entire history of how cosmic structure has evolved over the past 13 billion years. It is a simple but elegant effect, a subtle stretching of light that encodes the entire grand story of cosmic expansion. The vastness of the cosmos and the distances between its objects are so far beyond our everyday experience that we need a special set of tools to measure them. We cannot simply lay down a cosmic measuring tape. Instead, astronomers have developed a clever, step-by-step method, a sequence of interconnected techniques that allows them to build up a scale of the universe, from our local neighborhood to the farthest reaches of observable space. This sequence is known as the cosmic distance ladder. Each step, or rung, of the ladder relies on the one below it for calibration, and each rung allows us to measure distances farther out into the cosmos. The very first rung, the foundation of the entire ladder, is parallax. This is a direct, geometric measurement that relies on no physical assumptions. It is the only truly direct way we have of measuring stellar distances. As the Earth orbits the Sun, our vantage point on the nearby stars changes. We look at a nearby star in, say, January, and then again in July, when the Earth is on the opposite side of the Sun. The nearby star will appear to have shifted its position slightly, against the background of much more distant, seemingly fixed stars. By measuring the tiny angle of this apparent shift, and knowing the diameter of the Earth's orbit, we can use simple trigonometry to calculate the distance to the star. This method is incredibly precise, especially with modern space telescopes like Gaia, which can measure these angles with an accuracy equivalent to measuring the width of a human hair from 1,000 kilometers away. But parallax only works for stars that are relatively close to us, within our own Milky Way galaxy. For more distant objects, the parallax angle becomes too small to measure. This is where the second rung comes into standard candles. As we've seen, these are objects whose true, intrinsic brightness we know. The first and most crucial of these are the Cepheid variable stars. These are a special class of giant, pulsating stars. They rhythmically expand and contract, and as they do, their brightness changes in a very regular and predictable pattern. In the early 20th century, the astronomer Henrietta Leavitt discovered a remarkable property of these stars: the period of their pulsation. The time it takes for them to go from bright to dim and back again is directly related to their absolute luminosity. The faster they pulse, the dimmer they are. The slower they pulse, the brighter they are. So, if you can measure the pulsation period of a Cepheid, you can immediately know how bright it truly is. And by comparing its true brightness to its apparent brightness in the sky, you can calculate its distance. Astronomers first calibrate this period luminosity relationship by finding Cepheids in our own galaxy, whose distances have been measured with parallax. Once calibrated, Cepheids become a powerful tool. They are bright enough to be seen in other, nearby galaxies, allowing us to measure distances out to about 100 million light-years. It was Edwin Hubble's discovery of a Cepheid in the Andromeda Nebula that proved it was a distant galaxy in its own right, and dramatically expanded our conception of the universe. For the third rung, to reach even farther distances, we need an even brighter standard candle. This brings us to the type a supernova. As we discussed, these are the thermonuclear explosions of white dwarf stars, and they all reach a very consistent and brilliant peak luminosity. We can calibrate the true brightness of these supernovae by finding them in the same galaxies where we have also measured the distance using Cepheids. Once we know their true brightness, we can use them to measure distances to the far corners of the cosmos. Because a single supernova can briefly outshine its entire host galaxy, we can see them billions of light years away. They are the lighthouses that allow us to survey the most distant reaches of the universe and to measure the history of cosmic expansion itself. The cosmic distance ladder is a triumph of astronomical ingenuity. It is a delicate and intricate construction where each rung must be carefully placed upon the one before it. Any small error in an early step can propagate upwards and become a large error in the final distances. But through decades of careful, patient work of cross-checking with different methods, and refining each and every step, it has provided us with a robust and reliable map of our universe. It is the framework that allows us to transform a two-dimensional picture of the night sky into a three-dimensional, dynamic, and expanding cosmos of breathtaking scale and profound depth. As we journey through this vast and expanding cosmos, our gaze is always limited. There is a boundary not of space, but of time. a horizon that encircles us, defining the edge of the universe we can ever hope to observe. This is the cosmic horizon. It is not a physical wall or a celestial barrier. It is a consequence of a simple and profound fact: the universe has a finite age, and light travels at a finite speed. Since the cosmos began approximately 13.8 billion years ago, light has only had 13.8 billion years to travel through space. Therefore, we can only see the objects whose light has had enough time to complete its epic journey and reach our telescopes. Any object that lies beyond this boundary is, for now, invisible to us. Its light is still in transit, a silent messenger, still racing through the expanding darkness, but yet to arrive. This horizon defines our observable universe, a vast sphere with us at its center. And every observer, on every planet, in every galaxy, has their own unique cosmic horizon, their own personal bubble of the visible cosmos. As time passes, our horizon gently expands. With each passing year, we can see one light year farther into space. In 1,000,000 years, our descendants will be able to see light from regions 1,000,000 light years more distant than we can today. The universe is slowly and patiently unveiling more of itself to us. But there is a tension, a cosmic race at play. While our horizon is expanding, the universe itself is also expanding, and that expansion is accelerating. Galaxies that are very far away are being carried away from us by the stretching of space-time at incredible speeds. There is a point, a distance, beyond which galaxies are receding from us faster than the speed of light. The space between us and them is being created so rapidly that the light they emit towards us can never overcome the ever-widening gulf. These galaxies are forever beyond our reach. Even though our horizon will continue to expand, it will never be able to catch up to them. So, the cosmic horizon is a soft and shifting boundary. It reminds us of the profound limits to our knowledge. It teaches us a form of cosmic humility. Beyond this veil of time and distance lies a vast, and perhaps infinite, unseen universe. Countless more galaxies, more stars, more wonders, whose existence we can infer, but whose light we may never see. It is a silent and constant reminder that the universe is always grander, more mysterious, and more vast than what we can ever hope to observe. It is an invitation to wonder, not just about what we can see, but about the immense and silent reality that lies forever beyond our view. From the almost unimaginable scale of the cosmic horizon, let us now drift our attention inward to something almost infinitesimally small, yet profoundly important: the tiny, ethereal grains of cosmic dust. Space is not perfectly empty. Drifting in the vast, cold regions between the stars are clouds of gas, and mixed within them are microscopic particles of solid matter. This is cosmic dust. These are not the familiar dust bunnies you might find in a quiet corner. These are specks of matter, unimaginably small, typically smaller than the particles in smoke. They are made of elements forged in the hearts of long, dead stars. Tiny crystals of silicates, like sand or olivine. Complex organic molecules rich in carbon, like polycyclic aromatic hydrocarbons, and tiny flakes of graphite or soot. This dust is the ash of stellar fires. It is born in the cool, outer atmospheres of dying, giant stars. As these stars swell and cool in their final phases, elements in their atmospheres can condense into solid grains, like soot forming in a chimney. This newly formed dust is then gently blown out into space, by the star's stellar wind. More dust is created in the violent, fiery crucible of supernova explosions. When a massive star detonates, the expanding cloud of debris is so hot that new elements are forged, and as this cloud expands and cools, some of these elements condense directly into solid dust grains. This is the cosmic cycle of matter. Stars live, they die, and they seed the universe with the raw materials for the next generation. And these tiny, insignificant, seeming grains of dust play an absolutely vital role in the life of the cosmos. They are the catalysts for creation. Within the great, cold clouds of interstellar gas, dust is the key to forming new stars. As a cloud begins to collapse under its own gravity, the gas would normally heat up, creating an outward pressure that would resist the collapse. But the dust grains act like tiny, efficient radiators. They absorb the heat from the colliding gas atoms and then re-radiate it away as infrared light, which escapes from the cloud. By cooling the cloud in this way, the dust allows gravity to win. The collapse can continue, and the core of the cloud can grow dense and hot enough to ignite as a new star. Without dust, star formation as we know it would be incredibly difficult, if not impossible. And once a new star is born, the dust plays its second, equally miraculous role. The leftover gas and dust around the young star settles into a flat, rotating disk, a protoplanetary disk. And within this disk, the dust grains are the seeds of new worlds. They begin to stick together. Electrostatic forces, like the static cling that makes dust stick to a surface, pull the tiny grains together to form fluffy, fractal-like aggregates. These aggregates grow, colliding and merging to form pebbles, then boulders, then kilometer-sized planetesimals. And over millions of years, these planetesimals continue to collide and grow through a process of gravitational accretion, eventually forming the rocky cores of planets, moons, and asteroids. Every rocky world in the universe, including our own Earth, began its life as a collection of these tiny, humble grains of cosmic dust. The surfaces of these dust grains also act as tiny, microscopic laboratories. In the cold, diffuse environment of space, individual atoms can be very slow to find each other and form molecules. But when they land on the surface of a dust grain, they can skate around until they meet another atom and react. This surface chemistry is crucial for forming more complex molecules, including water, ice, methane, ammonia, and even the simple organic molecules that are the precursors to the chemistry of life. So these tiny specks of starlight soot are not just inert debris. They are the cooling agents for stellar birth, the building blocks of planets, and the protective nurseries for the universe's most complex chemistry. They are the quiet and patient architects of cosmic complexity. This pervasive cosmic dust does more than just build new worlds. It also shapes our view of the universe. It acts as a great cosmic veil, obscuring our view of what lies behind it. The same process that makes a sunset appear red, where dust and aerosols in the Earth's atmosphere scatter away the blue light, happens on a galactic scale. Cosmic dust is very effective at absorbing and scattering shorter wavelengths of light, like blue and ultraviolet light. This is why dense clouds of dust appear as dark, opaque patches against the bright backdrop of stars. They form the beautiful, dark nebulae that we can see with our telescopes. The famous Horsehead Nebula, or the intricate dark lanes that crisscross the bright band of the Milky Way. are all just shadows, cast by these immense clouds of interstellar dust. This cosmic fog can hide entire regions of our galaxy from our view in visible light. The very center of our Milky Way, with its supermassive black hole and its dense cluster of stars, is completely invisible to our eyes, shrouded behind thousands of light years of thick, obscuring dust. And this is true for other galaxies as well. Many of the most active and prolific star-forming galaxies in the distant universe are so enshrouded in the dust produced by their own frantic star birth that they are almost completely dark in visible light. They are hidden, cosmic cities whose brilliant light is trapped behind a veil of their own making. But this is not the end of the story. What the dust takes away with one hand, it gives back with another. The dust grains absorb the intense starlight from the young, hot stars embedded within their clouds. This energy heats the tiny grains up, and just like any warm object, from a hot stove to a living creature, the dust grains then radiate this heat away. They glow, but they don't glow in visible light. They are not hot enough for that. Instead, they glow in longer wavelengths of light, in the infrared. This is a profound and beautiful transformation. The dust acts as a cosmic converter, taking in high energy, visible and ultraviolet light, and re-radiating it as a gentle, low energy, infrared glow. And this infrared light, because of its longer wavelength, is not easily scattered or absorbed by the dust. It can pass right through the dense clouds and travel across the universe to reach us. So, if we want to see what is happening inside these dark, dusty clouds, if we want to witness the birth of new stars and planets, or uncover the most furiously star-forming galaxies in the early universe, we cannot use our eyes. We must build infrared eyes. Telescopes like the Spitzer, Herschel, and now the magnificent James Webb Space Telescope are designed to see this invisible, infrared universe. When we look at a familiar object, like the pillars of creation, with an infrared telescope, the dark, opaque columns of dust become translucent and ethereal. And we can see, for the very first time, the brilliant, newly formed stars that are hidden deep inside them, glowing like embers in a cosmic fireplace. When we point our infrared telescopes at a seemingly blank patch of sky, we can uncover a treasure trove of distant, dusty galaxies, glowing brightly with the light of 1 trillion hidden stars. The dust is both a curtain and a lantern. It hides the universe, and it also illuminates it. It reveals a hidden layer of reality, a warm, glowing cosmos of birth and creation that is happening all around us, just beyond the narrow range of light that our eyes are able to see. It is a quiet reminder that the universe is always more complex, more layered, and more beautiful than it first appears. And so, our gentle journey through the cosmos for tonight draws to a quiet close. We have drifted on currents of thought, from the familiar sands of our own world to the uncountable stars that fill the universal ocean. We have witnessed the graceful, silent expansion of space-time itself and heard the faint, microwave echo of the first light. We have touched the invisible architecture of dark matter and felt the mysterious, accelerating push of dark energy. We have wandered through our own spinning, starlit city of the Milky Way, and watched the slow, majestic dance of colliding galaxies. We have seen the brilliant beacons of quasars, shining from the dawn of time, and felt the silent rain of ghostly neutrinos passing through us from the heart of our own sun. From the absolute, physical limit of our cosmic horizon to the tiny, vital grains of stardust that build new worlds, we have explored a universe of staggering scale and profound and quiet beauty. And in all this vastness, in all this silent, ancient light, there is a deep and comforting connection. The cosmos is not something separate from us. We are not just observers looking in from the outside. We are a part of it, a living, breathing, and quietly thinking part of it. The carbon in our cells, the oxygen that fills our lungs, the iron that flows in our blood, all of it was forged in the fiery heart of a star that lived and died billions of years ago. The water that makes up our bodies was formed from atoms born in the first 3 minutes of the universe. We are assembled from the ashes of ancient suns. We are woven from the fabric of space-time. We are, in the most literal and beautiful sense, stardust given voice and wonder. As you rest now, the universe continues its silent and patient unfolding. Somewhere, deep in a dusty nebula, a new star is igniting. A photon that began its journey 1 million years ago is just now arriving at a distant world. Our own solar system continues its long, graceful arc around the galactic center. All is in motion. All is calm, and you are a small, peaceful part of this vast and radiant whole. Thank you for exploring the quiet wonders of the cosmos tonight. May your rest be deep, and your dreams be filled with a soft and distant starlight. Good night.